This is an interesting part. Although these are digital systems, I don't know, I'm going to say something very trivial to anybody in electronics, but maybe somebody who's just surfing on this might think that since the chip is digital, then getting any info on how it's done and what it works, it's just a matter of perfect digital copy and stealing information digitally out of it, but it's not true. Although we can push information and register, we can write to certain registers or parameters on the chip. The only thing we know about it is the voltages that change over time in the outputs of the chip. So it doesn't mean a perfect copy. This is one very tricky area, and it's when you record a sound chip, most people get that, and this is typical of any off-the-shelf sound card. This is what you're going to record, either if you're plugged in a Game Boy or directly on the chip. And you see it's not really a square wave, but in reality, it is. It's just you don't have the right tools to see it. This is using an oscilloscope, and this is the two photos are a square wave, a pulse wave of the SID chip. And it's just that I made this like a year ago. Your test sound card, of course, is typically AC coupled, so it doesn't pass DC, so you can't see that thing. See, that's a SID chip, and from the low to the high, you have like it starts from 9 volts to 11 volts. So there's a huge DC offset. So whatever that goes into a electrolytic capacitor, like it's just shit. But it's not gonna a plus with different. So the capacitors and the impedance mismatch with the sound card is just wrong. So you're going to get this, and many people on the net, which are more programmers and emulator writers, will tell you that it's because the chip is imperfect that it does that. It just stands so far. Little scale might be able to talk to you, to argue with this. It's just a problem with the way you monitor stuff. So it's good to have both an oscilloscope and an AC coupled sound card when you're recording patterns and stuff, because both are used and you're useful for two different areas. A digital oscilloscope will have oftentimes a very limited amount of memory. So if you want to capture a very long stream of bytes or bits like a linear feedback shift register, it's going to be difficult with that. But if you record with a sound card, then you have, of course, unlimited hard drive space. And you just dump it there and analyze it later. Of course, if you had a logic analyzer that costs hundreds of dollars, then you have both at the same time. But I don't have access to that. When you have a chip, from all the chips I've analyzed so far, these are roughly the things you want to look for because they're all really similar. They all came out at the same time, but they all have their ports. Of course, the number of voices they have might be different. The types of voices and the waveforms on each of those channels, and especially some chips have some channels that output on physical pins like the AY and the AS. If you write to register, the register writes and register delay might only be important for people who actually write emulators and not exactly for people who just want to make a synthesizer based out of those sounds. But it really makes an importance if you write an emulator because it needs to be plot accurate. The peaks needs to phase a certain way, and phase cancellation needs to, if you have multiple channels and you mix together, it needs to be absolutely like the games, otherwise the sound or the tracks are not going to sound the same. Yeah, sometimes some register writes have a delay, but again, these are very advanced subjects. They're only interesting to people who are going to write emulators. Voice mixing, if you have, sorry, maybe going a bit too fast, but I have a huge amount of stuff. If you have multiple voices that spew out on one channel, either it's going to be mixed as a plus, which is basically one voice will say, example, output from 0 to 1 volt, and if you mix 2 and it goes to 2, then you know it's just plussing voltages. If they're ANDing together or ORing, you'll see that how many voices you're going to put, they're always going to output the same voltage on the oscilloscope, but the bits are going to add differently. This is the part that I really like, and it's a favorite of many people in the emulation scene, is how to understand and record it under the linear feedback shift registers. Anybody rings a bell to somebody here? Of course, little scale. This is a small, well, initially, I'll try to backtrack a little. Initially, in the early days of computing, generating random numbers was not very easy because it's not a trivial thing, and it's still heavily a very interesting computing challenge right now to make perfect random number generators. And we're getting close now, and we're getting, because for casinos and all sorts of stuff, you need to have very precise and non-repeatable random numbers, which is not the case with this, because it's all about repetition. So it's a small amount of RAM in the chip, and I don't want to do the maths about it. There's a very good Wikipedia history on it. So basically, I have a few bits, and they shift and they feed back to the end with XOR or something with multiple tabs. So it's not for today, especially not after yesterday evening. So what feedback or noise looks like, you need to play that, your first one. It's going to sound like, because there's no sound in this demo. So I actually on purpose recorded playback on this. This is the +4 noise channel. I've actually on purpose played it very low so that I was able to record all the possible steps that were. You can show them. I'll let you. Yeah. But of course, in typical consoles, you play it much faster to make the hi-hats and the snares and stuff. But I mean, if you want to do perfect emulation, you need to understand what you do. So basically, you sample all this and just do mathematical. I mean, you saw that these things look like it was made out of some logic underneath it. So basically, you calculate the amount of samples in between each 0 and 1 transition or 0 cross image I use. And so you just make bins out of that. So we see that depending on the sample rate that you're going to use to record the sample, it's going to be different. But 439 was the thing that was most common. If you see a pattern here, you'll see that this is a bin, and of course, roughly double that is here, and so forth and so forth. So if you take all those information and you divide that with the lowest possible common denominator, you'll get your nice bit pattern here, which in this case is 255 bit long, so it's a power of 2 minus 1, which tells you exactly, okay, especially if you have multiple series of them, one after the other that were connected, you know you're really on the right track. So from then on, you can take the Berkeley-Mason algorithm that I just learned about like 2 days ago. And with this bit pattern, you can find out how to generate this from a small string of bits instead of having all that in either your emulator or in your program, which is what I do. But whether you have these series of bits or you have the math behind them, it's going to end up sounding the same unless you really know how to program.